Astronomers were combing through new James Webb Deep Field data when something strange appeared. Not a galaxy, not a burst, a single razor-thin spike in the infrared spectrum. Clean, structured, and coming from over 12 billion light-years away. At first, they assumed it was noise, but it kept showing up, and signals like this aren't supposed to exist out there.
They pointed the most powerful telescope ever built into the darkest patch of space. They expected silence, faint galaxies, ancient light. Instead, they found something that doesn't fit. A signal, too structured, too bright in the wrong place, too strange to ignore. And now, astronomers are asking a question they never thought they'd need to ask this soon. What exactly did the James Webb Space Telescope just detect? Launched in 2021, the James Webb Space Telescope, or JWST, was designed to look deeper into the universe than ever before. Unlike its predecessor, the Hubble Space Telescope, which sees mostly visible light, Webb observes the cosmos in infrared. That means it can peer through cosmic dust. It can see heat signatures, and it can detect some of the oldest light in existence. Its mission was clear: study early galaxies, analyze exoplanet atmospheres, and push the limits of what we know about cosmic origins. But science doesn't always stay inside mission parameters. Recently, researchers analyzing deep field data from JWST noticed something unusual buried in the infrared spectrum of a distant object. At first, it looked like noise, the kind of statistical oddity that appears when you collect massive amounts of data. But this wasn't random. The signal showed repetition, pattern, a narrow frequency band that didn't match expected astrophysical emissions. It wasn't coming from a known pulsar. It didn't resemble the chaotic signature of a quasar. It wasn't behaving like background radiation from the early universe. And that's where things got interesting. When astronomers observe distant galaxies, they rely heavily on spectroscopy. By breaking light into its component wavelengths, they can identify chemical elements, hydrogen, oxygen, carbon, each leaving a unique fingerprint. JWST is especially good at this. Its sensitivity allows it to detect faint absorption and emission lines billions of light-years away. But this signal wasn't lining up with known spectral lines. Instead of broad emissions typical of stellar processes, researchers found a sharply defined spike. Clean, isolated, persistent across multiple observations. That's not how natural astrophysical processes usually behave. Nature tends to be messy. The team double-checked calibration. They ruled out instrumental glitches. They compared data across different observation runs. The signal remained. Now, before jumping to dramatic conclusions, scientists do what scientists always do. They look for mundane explanations first. Could it be a previously unknown type of stellar remnant? A rare molecular cloud effect? Gravitational lensing amplifying something ordinary into something extraordinary? These possibilities are still on the table. But here's the twist. The signal appears to originate from a region associated with a galaxy over 12 billion light-years away. That means we're seeing it as it existed when the universe was less than 2 billion years old. At that time, galaxies were chaotic. Star formation was rapid. Black holes were growing aggressively. Heavy elements were scarce. The universe was not calm or orderly. So why would there be such a clean, narrowband emission? Narrowband signals are unusual in natural astrophysics. Pulsars emit beams, yes, but their signals pulse rhythmically. Quasars produce immense energy, but across wide spectral ranges. Even fast radio bursts, those mysterious millisecond flashes first detected in 2007, don't behave like this. Speaking of fast radio bursts, observatories like the SETI Institute have long studied unusual signals to determine whether they originate from exotic astrophysics or, in the most speculative cases, artificial sources. But JWST doesn't observe radio waves. It observes infrared light. So whatever this is, it's not a classic radio transmission. Still, structured signals raise eyebrows. Decades ago, the famous WOW signal, detected by the Big Ear Radio Telescope in 1977, sparked similar intrigue. It was a strong, narrowband radio signal that appeared once and never repeated. It was never conclusively explained. Most scientists suspect a natural cause, but uncertainty lingers. The JWST signal is different. It's repeatable. It's embedded in infrared data, and it's far older than anything humanity has ever transmitted. So what could produce it? One hypothesis involves exotic atomic transitions under extreme early universe conditions. Perhaps high-energy radiation from an early supermassive black hole is interacting with primordial gas in a way we've never observed before. JWST has already surprised astronomers by finding surprisingly mature galaxies earlier than expected. Maybe this is another example of the early universe being more complex than models predicted. Another possibility involves gravitational lensing, when a massive object bends light from something behind it. Lensing can magnify and distort signals, sometimes creating arcs or duplicated images. Could lensing be concentrating a faint spectral feature into something sharper? Researchers are modeling this scenario now. There's also the possibility of unknown molecular chemistry. JWST has detected complex organic molecules in space before, even in regions where scientists didn't expect them. If an unusual molecule were present in abundance under early cosmic conditions, it might produce a spectral line we haven't cataloged yet. But here's the challenge. The frequency doesn't correspond cleanly to any known molecular transition, and that leaves a gap. In science, gaps are dangerous. They invite speculation. Online forums have already begun spinning theories. Alien megastructures, Dyson spheres, interstellar beacons. But professional astronomers are cautious, almost painfully so, because extraordinary claims require extraordinary evidence. JWST is sensitive, incredibly sensitive. That means even subtle data processing artifacts can masquerade as real phenomena. Independent teams are now analyzing the same dataset. Cross-validation is underway. Other observatories are being tasked with follow-up observations in different wavelengths. That's how science works. Slow, careful, relentless. If the signal disappears under further scrutiny, it becomes a footnote, an interesting glitch that helps refine data analysis methods. If it persists, then we may be looking at something genuinely new. And new in astronomy doesn't mean aliens. It means physics we don't yet understand. Remember when astronomers first discovered pulsars in 1967? The signal was so regular that researchers jokingly labeled it LGM-1, little green men. They quickly realized it was a rapidly spinning neutron star, a natural explanation, but one that expanded our understanding of stellar evolution. What if this JWST signal is our generation's pulsar moment? The telescope has already rewritten textbooks. It has revealed galaxies forming earlier than models allowed. It has detected water vapor in exoplanet atmospheres. It has captured images of star birth in unprecedented clarity. Its instruments, including the near-infrared spectrograph and mid-infrared instrument, are capable of dissecting cosmic light with extreme precision. When they see something odd, it's worth paying attention, but it's also worth being patient. Astronomy operates on cosmic timescales. Months of analysis may pass before a paper is peer-reviewed and published. Data will be reprocessed. Alternative explanations will be proposed and challenged. The scientific community thrives on skepticism. That's its strength. Right now, the leading interpretation leans toward an unknown astrophysical process, possibly tied to early black hole growth or unexpected chemical compositions in primordial galaxies. Yet even that is profound, because if our models of the early universe are incomplete, this signal could help refine them. It could adjust our understanding of how the first structures formed. It could influence simulations of galaxy evolution. In other words, whether mysterious or mundane, it matters. There's something poetic about it, too. JWST was built to look back in time, to capture ancient light traveling billions of years before Earth even formed. And in doing so, it has stumbled upon a whisper from the early cosmos that doesn't quite fit our expectations. Not a message, not a beacon, but a puzzle. And puzzles are how science advances. The universe has a history of humbling us. Every time we think we've mapped it neatly, it reveals another anomaly. Dark matter, dark energy, fast radio bursts, interstellar objects like Oumuamua. Each discovery began as something that didn't make sense. Then came the slow, methodical work of understanding. Maybe that's what we're witnessing now. The first glimpse of a phenomenon that will feel obvious in 20 years. A new category in astrophysics textbooks. A footnote in future lectures. Or maybe it will fade under better calibration and sharper analysis. Either way, JWST has done exactly what great instruments are meant to do. It has pushed us into the unknown. And somewhere, 12 billion light-years away, a galaxy from the dawn of time continues to emit light that has traveled across cosmic history just to reach our detectors. We caught it. Now we have to figure out what it's trying to tell us. Not as a message, but as physics. Because the universe doesn't speak in words. It speaks in signals. And this one doesn't make sense. Yet.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.